Gravity is a universal force of attraction that exists between any objects with mass. Gravity explains why objects fall towards the Earth's surface. Gravity is the force that causes celestial bodies to orbit each other. The greater the mass of an object, the stronger its gravitational pull. Gravity is an invisible force that pulls objects toward each other. All objects with mass exert gravity. The more massive an object, the stronger its gravitational pull. Gravity is a fundamental force of nature, responsible for holding celestial bodies together. The Earth's substantial mass generates a significant gravitational force. The strength of gravitational force is directly proportional to an object's mass. The gravitational force exerted by Earth is strongly felt due to its large mass. Objects with smaller masses experience a weaker gravitational pull compared to Earth. Gravitational force is a fundamental force that attracts objects with mass towards each other. Newton's law of universal gravitation quantifies the gravitational force between two objects. The gravitational force, F, is directly proportional to the product of the masses, m₁ and m₂. The gravitational force, F, is inversely proportional to the square of the distance, r², between their centers. G represents the gravitational constant, a universal value. The formula F equals G Cheng2 m₁ Cheng2 r². Mathematically expresses Newton's law of universal gravitation. Gravitational force is directly proportional to the product of the masses of two objects. Larger masses result in a greater gravitational force between objects. Increasing the mass of either object increases the gravitational force. The relationship between mass and gravitational force is linear. Newton's law quantifies the mass dependence of gravitational force. Gravitational force is inversely proportional to the square of the distance between objects. Greater distance between objects results in a weaker gravitational force. The relationship between gravitational force and distance follows an inverse square law. Doubling the distance reduces the gravitational force to 1/4 of its original strength. This inverse square relationship is fundamental to understanding gravitational interactions. Simulations accurately demonstrate the effect of distance on gravitational force. Gravity is the force that keeps objects grounded on Earth. Gravity causes objects to accelerate downwards towards the Earth's surface. The rate of acceleration due to gravity is approximately 9.8 meters per second squared. Without gravity, objects would float freely instead of remaining on the ground. The strength of gravity depends on the mass of the object and the distance from the Earth's center. Gravity is essential for maintaining our atmosphere and preventing us from drifting into space. Gravity is the force that causes raindrops to accelerate downwards from clouds. Without gravity, raindrops would not fall to the ground. The size and shape of raindrops are influenced by gravity and air resistance. The constant pull of gravity causes raindrops to consistently descend. Raindrops accelerate until air resistance equals gravitational force, reaching terminal velocity. Gravity ensures that precipitation, in the form of raindrops, reaches the Earth's surface. Gravity is the force that retains Earth's atmosphere. Without gravity, the atmosphere would dissipate into space. The atmosphere is crucial for life, providing breathable air and shielding from harmful radiation. Gravity's consistent pull ensures the atmosphere remains a stable and protective environment. Galileo's experiment demonstrated that objects fall at the same rate irrespective of their mass in a vacuum. Air resistance is the key factor, causing variations in the falling rates of objects with different shapes and masses. In the absence of air resistance, gravitational acceleration is constant for all objects near the Earth's surface. Galileo's findings challenge the prevailing Aristotelian view that heavier objects fall faster. In a vacuum, objects are not affected by air resistance. Gravity exerts the same acceleration on all objects in a vacuum, regardless of their mass or shape. The hammer and feather fall at the same rate within the vacuum. The hammer and feather strike the ground simultaneously in the vacuum. This demonstrates that gravitational acceleration is independent of an object's mass or shape in the absence of air resistance. Galileo's experiment disproved the Aristotelian belief that heavier objects fall faster. The Moon's gravitational force is approximately 1/6 that of Earth's. Lower gravity allows astronauts to jump higher and move with greater ease on the lunar surface. Reduced gravity impacts locomotion, enabling longer strides and reduced effort for movement. The difference in gravity affects the weight of objects. An object weighing 60 kilograms on Earth weighs only 10 kilograms on the Moon. Astronauts in orbit experience microgravity. Microgravity occurs because astronauts are in free fall around the Earth. Free fall involves constant acceleration towards Earth. Astronauts in orbit are constantly accelerating towards Earth, but never hitting the surface. The sensation of weightlessness is due to the continuous state of freefall. Black holes possess extremely strong gravity due to their immense density. The gravity of a black hole is so intense that nothing, not even light, can escape its pull. Immense density is the primary factor contributing to the extreme gravitational force of black holes. The event horizon defines the boundary beyond which escape from a black hole is impossible. The gravitational pull of a black hole increases exponentially closer to its center. The inability of light to escape a black hole results from the extreme curvature of spacetime. Gravity is the fundamental force that binds objects with mass or energy together. Gravity holds us to the Earth, preventing us from floating into space. Gravity maintains the planets in their orbits around stars. Gravity is responsible for the large-scale structure of the universe, shaping galaxies and clusters. Without gravity, the universe as we know it would not exist. Albert Einstein's theory of general relativity provides a deeper understanding of gravity. General relativity explains gravity as the curvature of spacetime caused by mass and energy. Spacetime curvature dictates how objects move within a gravitational field. Einstein's theory revolutionized our understanding of gravity, moving beyond Newtonian mechanics. General relativity has significant implications for astrophysics and cosmology. The curvature of spacetime is a fundamental concept in understanding the universe's structure and evolution.